Okay, in this section, we're going to introduce a new function. So we've already had linear, quadratic, polynomial, and rational functions. We have two more functions to cover. So we're going to get started with exponential functions. Now, with all of those other functions, we always recognize the function based on where the x was or what the exponent on the x was. So to recognize exponential functions, it's fairly straightforward because what will happen is the variable will appear in the exponent position. Now, when it comes to looking at an exponential function, remember that whatever is being raised to the power, so when I look at this function here, f of x equal to 5 to the x, the 5 is the base, and the x is the exponent. Now, I can also have functions, exponential functions, where I have an algebraic expression as the exponent. Like here where my base is 8 and my exponent is 2x minus 3. So we'll work on those types of functions as we go along. Now, the base of an exponential function can be any number that's bigger than 0. We don't want our base to be 0 because 0 to any power is just 0. And we also don't want our base to be 1 because if I raise 1 to any power, I just get 1. So that wouldn't have the characteristics of what an exponential function is. Now, besides any number greater than 0, there is one irrational number that shows up as a base quite frequently when we're talking about exponential functions, and that's the irrational number e. Now, e is an irrational number, meaning that there's no fraction equivalent to it. It's a decimal that continues to go on forever and ever, similar to pi. You know, we recognize pi as being 3.14, but we know that that decimal goes on forever. So e is associated with 2.7, but that decimal goes on forever. So e is just a base that shows up a lot. It doesn't get treated any different than if my base was 5 or my base was 8. So when you see an exponential function like this is an exponential function because x is in the exponent position. It has nothing to do with the base e. So when you're working with exponential functions, don't worry about when that e shows up. You don't want to treat that e any different than you would if the base was 5 or 15 or 25. It'll get treated just the same. Okay, we'll talk more about e's as we go through, of course. So let's take a look at the graph of an exponential function. So what we're going to do primarily in this lesson is learn how to graph exponential functions using transformations. So if you remember back in our transformation section, we learned how to identify whether a curve was being shifted up, down, left, right, or reflected. And we worked off of a basic shape to get a transformation drawn. So there is a basic shape for an exponential function, which you can see on the screen. This basic shape is what we're going to use to do our graphing of exponential functions. So let's start and talk about what this basic shape consists of. The first thing to note about the basic shape is that there is a horizontal asymptote. So that horizontal asymptote is identified in the graph by that dotted line. Now, when you look at the shape itself, if you look at the point that I have plotted, my point here is the y-intercept 0, 1, and that's the point that we're going to want to use in our transformation. So when we do our transformation, the two things we're going to actually draw in our graph before we draw the curve is we're going to plot that point wherever it may end up, and we're also going to draw where the horizontal asymptote would be. So those are the two things that we want to get drawn first on our curve. Now, as far as the shape of the curve, to the right of x equal to 0, to the right of that y-intercept, my curve continues to to climb very rapidly. So the further up you go, or the bigger the base on your exponential function, the faster that climb would occur. So the steeper that it would be. And then on the left-hand side of my y-intercept, the curve flattens out. And this curve is going to get closer and closer and closer to that horizontal asymptote, but it will never cross the horizontal asymptote or actually reach the horizontal asymptote. Okay, so a couple of things that we want to pull from this curve. These three items here, you're going to be asked about each time that you graph an exponential function. So the first thing is the domain. Remember, your domain are all of the x values that are allowed, or when you're looking at the graph, it's how far left, how far right the curve goes. So if you think about an exponential function, like let's say 5 to the x, think about any restrictions you might need to make on an exponent. And there aren't any. There are no numbers that I can't put in an exponent. And then also, if you look at the curve, you notice that it goes to the left forever, and it also goes to the right forever. Now it's going up, but it's also going slowly and slowly to the right. So the domain of any exponential function is always going to be all real numbers, or as an interval, -infinity to infinity. So in MyLabs Plus, it's not going to let you do the shorthand for all real numbers. It's going to want the interval -infinity to infinity. Okay, I'm going to skip over the range. We'll go back to that. I want to talk about the horizontal asymptote first. So the horizontal asymptote is that imaginary horizontal line that one branch is approaching. And in this case, in the basic shape, that horizontal asymptote is on the x-axis, and the equation for that horizontal asymptote would be y equal to 0. A horizontal asymptote always needs to be written as an equation because it is a line, and it's always going to be y equal to whatever the y value is that it's passing through. In the basic shape, that's 0. Okay, now let's do the range. The range is going to be how low my curve goes to how high my curve goes. So in the basic shape, remember that left-hand side is approaching the horizontal asymptote and getting very, very close to it. So our range is going to start at where that horizontal asymptote is. And then, of course, how high it goes, it keeps going up until infinity. Of course, you never get to infinity, but it's rising continuously. So my range is going to be from 0 to infinity, and that 0 is closed with a parenthesis because I don't actually reach that horizontal asymptote. So I don't know why my parentheses kind of tends to look like a bracket. I don't want that to be confusing. That is a parenthesis, never a bracket in the range for an exponential function. Okay, so let's take a look at some examples and get these curves in the examples drawn using transformations. Okay, one quick thing to note here is that when I'm using transformations, remember this is a quick sketch of the curve, one where I'm not plotting a bunch of points. What I want to move when I'm doing transformations is I want to find out where the horizontal asymptote is going to be located, and I want to move that one point, which is in the basic shape at 0, 1, I want to move that. So in the basic shape, my horizontal asymptote is at 0, and that one significant point is at 0, 1. So those are the two things I want to move first. One other general thing about transformations is that let's compare, let's say that I had y equal 8 to the x and I had y equal 5 to the x. If I were graphing these two using transformations, they would look basically identical to each other. In other words, when you're doing transformations, what your base is not going to have an effect on what your graph looks like. Now, of course, 8 to the x would climb faster than 5 to the x would, but we're not measuring that. We're not measuring how steep your climb is. So in general, 8 to the x and 5 to the x could look very much the same when you're doing transformations. So you don't need to really worry about what the base is. You just have to identify the transformations. Okay, so let's get to that example. So in this example, I want to sketch the curve e to the x plus 1 minus 3. So the first thing is I want to identify what the transformations are. And I've got something being added to my x there in the exponent. So remember that anything being added or subtracted to my x is a shift left or right. And remember, these are kind of anti-intuitive when you're looking at the ones on the x. So this plus 1 on my x is going to move my curve left 1 unit. Then I've also got a minus 3, and that minus 3 is to the whole function. So adding or subtracting to the whole function either moves it up or down, and in this case, it moves it down 3 units. So those are the two transformations I want to occur in this graph. So let's start with where we're going to plot that horizontal asymptote, or draw the horizontal asymptote. So in the basic shape, it's at 0. And if I move a horizontal line left, it doesn't change where that's at. So the horizontal asymptote is not affected by the move left, but it will be affected moving it down 3. So my horizontal asymptote is going to go down 3 units, and I want to draw in that dotted line at y equal to -3. Now let's move or plot where that point should be. So in the basic shape, the point is at 1, and I want to move that left 1 and down 3. So if I start here at 0, 1 and go to the left 1 and then down 3, that's going to put me right here. So when I go to sketch my curve, I did not have any reflections, which means that the shape of the curve is going to match the shape in my basic shape. So if we go back to this example and mimic that shape, my curve is going to end up looking like this. So there is my graph. I'm not going to pick on you. You're going to be picking from graphs that are drawn in MyLabs Plus, so your artistic ability isn't going to come into play when you draw these curves. So there is a basic shape for that particular function based on transformations alone. Okay, now I mentioned that you're going to be asked for the domain, the range, and the horizontal asymptote. So let's write what those are real quick. The domain is the easiest thing to do for an exponential function because all exponential functions have a domain of all real numbers, so -infinity to infinity. I always do my horizontal asymptote before my range because it plays a part in the range. So I'm going to write what my horizontal asymptote is first. And remember, we shifted it down to -3. So make sure you write it as an equation, y equals -3. And now my range, because my curve is above the horizontal asymptote, my range is going to be from the horizontal asymptote to infinity. So there's my curve. Okay, example number 2. We want to sketch the curve of -5 to the x plus 4. So again, let's identify what the transformations are. I don't have anything being added or subtracted to the x, but I do have this negative out in front of the 5. So remember, out in front of the whole function, that's going to be a reflection. And that reflection when it's out front is a reflection through the x-axis. So kind of the idea of flipping upside down. And then my +4 out here is going to move my curve up 4 units. So let's get our horizontal asymptote drawn. So the horizontal asymptote starts at 0 in the basic shape. And horizontal asymptotes are not going to be affected at all by reflections. So the reflection doesn't do anything. But I will have to move my horizontal asymptote up 4 units and draw in that invisible line. The next thing I want to do is figure out where my point that starts at 0, 1 in the basic shape. I want to figure out where that's going to move to. And this one will be affected by the reflection through the x-axis. So when I reflect that through the x-axis, remember it flips all the way over to here. So I'm now at -1, and then I want to go up 4. So if I now move this up 4, so 1, 2, 3, 4, that puts my point right here. So remember that when you're doing transformations, I want to do the same order that I would do if I put a number in for x and did the arithmetic. So the reflection would be first, then moving up 4. Okay, now we've got to draw our basic shape. But remember that I had a reflection through the x-axis, which means that my basic shape is going to be turned upside down. So if I turn that basic shape upside down, it's going to look like this. Now, one thing to point out about the two curves, this is an observation that you can rely on a little bit to make sure that your graph is mostly right anyway, is that notice that the point and the horizontal asymptote in both graphs are 1 unit apart. That will always be the case. Now you can see that sometimes the curve is above the horizontal asymptote, sometimes the curve is below the horizontal asymptote, but that point you plot and the horizontal asymptote will always be within 1 unit of each other. They'll always be 1 unit apart. So if your point is too far away, then you've done something wrong in terms of your transformation. Okay, domain, of course, all real numbers. The horizontal asymptote, we move the horizontal asymptote up 4. So my horizontal asymptote is at 4. And then I'm going to do my range. So this time my curve, my entire curve is below the horizontal asymptote, which means that my range is going to start from -infinity because it goes down forever. And when it comes up, it's going to get stopped by that horizontal asymptote at 4. Okay, let's take a look at one more curve. I wanted to make sure to get the reflections in because sometimes those cause the most trouble. So this one's got a reflection, but the reflection this time is on just the x. The negative is right in front of the x only. So this time my reflection is through the y-axis. So it is a left-right flip, so to speak. All right, so if we go and start plotting what we want to plot, if I start with the horizontal asymptote, my horizontal asymptote in the basic shape is at 0. And I mentioned already that horizontal asymptotes are not affected by reflections, which means that the horizontal asymptote stays right there at 0. Now, if I want to get that point plotted, we start with the point at 0, 1, and I can't reflect that through the y-axis. If I fold this curve on the y-axis, that point's going to stay right where it is. So that point remains there based on that reflection. But now remember how the curve is going to look. Let me draw in just a little bit of what the basic shape, remember the basic shape is like this, but we want to flip this left right. So that means this piece, this branch on the right, now needs to go on the left, and this little branch, the flattening out on the left, is now going to be moved to the right. So my curve is going to look like this. So let's take a look at what that domain, range, and horizontal asymptote would be. My domain, of course, never changes for any exponential function. The domain is always all real numbers. My horizontal asymptote never moved. So my horizontal asymptote is y equal to 0. My curve is above the horizontal asymptote, which means my range is going to be from the horizontal asymptote to infinity. Okay, we've got one more quick example to do in this section, and it has nothing to do with graphs, but you will have a word problem or two in homework, so I want to make sure that we took a look at that example. So notice here we've got a function that is an exponential function in this problem because my variable, in this case d, is in the exponent position. And let's see what we need to do. So that function describes the number of people in a college community where there's 1,000 students to begin with, and D is the number of days. And so we're trying to figure out how many people will have heard a rumor after 3 days. So they're giving us D equal to 3, and we're being asked to find N. So all we've got to do that is replace the D in the function with 3, and then we're going to want to get on our calculator to do this arithmetic. So do make sure that you have a calculator that has an E and your caret key for your exponent. So I'm going to do this in stages so that you can check yourself on your calculator as well. So I've got N is equal to 1,000. I don't want to do that. All I want to do is figure out at first what this exponent should be. So if I multiply 0.15 times 3, I get a new exponent of negative 0.45. So the next thing that I'm going to do is raise that E to the negative 0.45. So you should have on your calculator an E to the X key. That's the E that you want to use because when you hit that key on your screen, you'll see E and then a caret. And behind that caret is where you want to put the negative 0.45. So when I do that, what I get for this right here is 0.637628, and I'll stop it right there. But because it's an E, that decimal is going to go on forever. So now I want to do 1 minus that value. So on my next line, I've got my 1,000, and when I did that subtraction inside there, okay, let me see here. I'm going to do 1 minus that, and I get 0.362337. We'll stop it there. And then if I just multiply that by 1,000, of course, that's just going to move the decimal over 3 places. So I get 362.37. Now, in terms of the word problem, though, it asks me how many students. So we don't have any third of a student. That doesn't make any sense. So we would just chop it off here where it made sense and say that 362 students would have heard that rumor after 3 days. So do make sure you practice on your calculator, that you're able to evaluate E's Real quick, I'll just give you a couple to practice. Like I don't know what I'm doing. If I take e to the fifth and e to the negative third. So if I raise e to the fifth power, I get 148.41. And if I raise e to the negative third, I get 0.049787. So check that with your calculator and make sure that you're okay with those keystrokes. And if you run into trouble, let me know. Okay, so that's all you're doing in 4.1. Mostly it's the transformations of the functions and getting used to the E. It'll have you do a couple of things on your calculator and then maybe a quick word problem or two at the end. Please feel free to email me or use the Ask My Instructor key or tab or button, whatever, in My Labs Plus if you have a question on a specific homework problem.